So, what is the physical seed of thought? What is the source of our emotions, our decisions making, our passions, our pains, and everything else? Well, it's the brain, and it's said to be the most complex mechanism in known universe. You might expect, given all it is and given all it does, that it will look very pretty, full of shimmering lights and glass tubes and mysterious colors. But in fact, it looks really kind of gross. It's look at the 3 days old meatloaf. It's grey when taken out of the head, and inside the head it's bright red because of all the blood. In fact, it turns out very surprisingly that the source of our mental life, of our conscience, is meat. In fact, you could eat it. People have eaten brains. I've had brain with cream sauce. Non-human brains, mind you, but I've had brain with cream sauce. It's not bad, but it makes puzzle all the more harder. How can this fleshy thing give rise to mental life? That's the questions I want to explore in this lecture and the rest of the lectures. I want to do so by starting with the smallest relevant parts, different parts of neurons. Then explore how the neurons are connected together, how they are wired up, how they form different substance of the brain, like the hypothalamus and the frontal lobe. Finally, talking about the brain and the larger perspective, looking at two halves of the brain, the left half and right half, and how they interact. Now, there's a lot of stuff in the brain, a lot of chemical stuff, a lot of different parts, but where the action is, the part that does thinking, the part that is the focus of most of our research, is the neurons. It's not an accident that calls a study of the biological basis of those neuroscience, because it all comes from the neurons. So you can see here pictures of neurons interacting together. Here is diagrams that depict a typical neurons. So what you see is the dendrites, and dendrites receive signal from other neurons, either excitatory like plus or inhibitory minuses. Then they get to the cell body, which sums up their pluses and minuses. When you reach a certain threshold, a central amount of pluses, there is neutral firing. Firing takes place through the axon. The axon is much longer than dendrites. In fact, for some motor neurons, it's very long indeed. That's axon running from your spinal cord all the way to your big toe. You could think of it in the relevant size of thing in terms of a basketball and a 40 miles garden house. Surrounding the axon is what called a myelin sheath. The myelin sheath is, if you can think of it as insulation, as fatty tissue, like insulation on a wire. So the information comes through the dendrites and summed up in the cell body, and it's transmitted through the axon. So what neurons do, it's they sum up the transmit information, even though that's a lot of them. By some estimate, it's 100 billions, or the estimate tend to be very different and very raw, but there's billions upon billions of neurons, and they connect to thousands, maybe tens of thousands of other neurons. So the fact that you have something in the degree to complexity, this degree structure which there is no way to replicate in any machine, the numbers are just too big, is why people might describe the brain as the most complicated machine in the universe. At least this is fitting. It's made of meat maybe, which is kind of disappointing, but at least it shows its incredible internal structure. So neurons come in three flavors. There is a sensor neurons which take in information from the environment, from the external world. There is motor neurons which go from the brain out to our motor control. So if you touch something hot and you feel the pain, that's in sensor neurons. If you rant your hand back or you reach for something, that's motor neurons. Finally, it's interneurons, which connect different neurons without making contact with external world, either through sensations or through motor actions. Now the main thing to think about for neurons, and neurons firing is it all or nothing. It's like firing a gun or sneezing. Neurons enter fire or they don't. Now you might think that's a little bit strange practically when you think about sensory neurons because your experience seems to be a continuum. So you have sensory neurons in your eyes and you can distinguish from a very dim light and a very bright light. You have sensory neurons in your fingers and you could distinguish between gently touch something versus begin stable on the tip of your finger or something. But still the neurons are all or nothing. The way we got to this continuity of experience is that neurons can code for an entity in different ways. So one way is in the term of the number of neurons that fire. If X neurons correspond to a mind experience, X times, then neurons may correspond to an intense experience. Another factor is the impulse frequency of individual neurons. An individual neuron might denote a mild sensation by doing fire, 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 fire. Well, it might denote an intense situation with fire, 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 fire. So you have neurons, and the neuron talk to each other. They talk to each other because of axon and axon. One neuron will communicate with the dendrites to another neuron. A long time ago, people used to think that neurons were wired up together like a computer, but in fact, neurons don't actually touch one another. There is a gap between the axon terminal of one neuron and the dendrite of another one. A very tiny gap, typically of like one ten thousandths of a meter wide. This gap is known as synapse. When one neuron fires, the axon release neurotransmitters. There are chemicals that spot out over the gap and affect the dendrites of other neuron. As I said before, the effect of the neurotransmitters could be excitatory, which is that they raise the energy, so they increase the likelihood of a neuron firing or inhibitory, so that they bring down the likelihood of a neuron firing, so that they bring down the likelihood of a neuron firing. That's interesting, is that different neurons shoot out different neurotransmitters, so they have different effects of other neurons that they made contact with. In fact, a lot of psychopharmacology both attempts to cure various psychological or psychical disease by giving medicine or recreational psychopharmacology designed to increase pleasure or different form or sometimes help people to work or help people focus works by filling with neurotransmitters, and this can be either agonists. They lower down intensity of things by building to the dendrites, making it hard to create new neurotransmitters, or they can increase the amount of neurotransmitters available in different ways, agonists. So you're either pumping up the volume or turning down the volume. So you think about different drugs and their effects. There is a curare. Curare is a drug that's used by South American Indians. It's antagonist. It blocks motor neurons from affecting their muscles fiber. It keeps your mouth motor neurons from working, and that it does is it paralyze you. And at large enough doses, it's kill you because motor neurons also keep your heart beating. So shuts it down and you die. It's alcohol. No, alcohol also has an inhibitory effect. You might think that's strange because when you drink alcohol, I get all execute and happy and goofy, but you have to keep this in mind. Here, the way alcohol works is it inhibiting part of your brain that does the inhibition. So you have part of the brain that say, don't say that to other person, keep it your pants on, stop yelling. And alcohol basically inhibiting that part of the brain, making you more exuberant. Then, over the course of think, it's a course of drinking too much, it's also inhibiting other part of the brain. So you can pass out and fall on the floor, and at large enough doses die. So, both curare and alcohol, it different ways bring it down. Another drug brings it up. So amphetamines, for instance, increase the amount of norepinephrine, which is another neurotransmitter that's responsible for generic gain arousal. And this is how drugs like speed or cocaine works. Other drugs like protaza or L-dopa influence neurotransmitters in ways that they increase, for instance, the supply of dopamine or serotonin, which can be relevant for issues like Parkinson, which seems to be related to too little dopamine, and depression, which is related to too little serotonin. So, their drugs work by influence neurotransmitters, either by directly pumping in more neurotransmitters or increase the CP of different ways or stopping them from having effects by beating them or sticking them up in different ways, but they work through the effects of neurotransmitters. So the more general idea is the way neurons lead to thinking is what they form clusters or network. Their clusters and networks are computational devices that do interesting things like recognizing face, or walking upright, or understanding sentence, or doing math, or experience great sadness, or falling in love, and so on. We know now that this is possible because we create computing machines that works in certain ways. That if you wire up a computing machine in certain complicated ways, I can do mathematics, play chess, do flight simulators, and so on. So, you may be interested in the project of computational neuroscience which try to ask the questions how are neurons wired up to do interesting things and use our success at computer knowledge theory as model. Then sometimes take the inference the other way around, which is you can see how people do it, and then uses knowledge of how people do it to create computational system that can do it as well. So, how is the brain wired up? Well, you might imagine that it's wired up like a portable computer, like a laptop, like the sort of computers they are looking at now. In some regard it is, but there is a couple of reasons why it can't be, and both of them have to do with how well the brain works. So, first, the brain is highly resistant to damage. If you get a knife to the brain, if you get damage to the brain, it won't typically shut down the whole system. The information and capacitor is somehow disturbed across neurons in such ways that makes them extremely resistant to damage. While in contrast, somebody could open up the back of your laptop, pull out a chip, and the whole thing is ruined. The whole thing will stop working. But the brain is wired up in a certain way that makes it highly resistant. The second thing is the brain is wired up in such a way that makes it work very fast. So computers can do millions of operations per second because they're purely electrical, but brain tissue much slower and can speed the time to do many steps. So, to put it in a different way, if your brain was wired up like a computer, it would be so slow to be eternally usable. It has to be wired up in a way that's more efficient, that allow for the slowness of brain tissues and neurotransmitters and can still compute things as a level, at a human level, which is often blindly fast. Because of this, there has been a huge interest in massive parallel system and complicated neural works, which are wired up as we believe the brain does. As such, we are helping computers to do things based on our understanding of the brain that they could never do before. The details of this is something we're going to talk about throughout this course. We are not actually going to end up explaining differently capacities directly in terms of neurons because we can't and because we want it to have higher level expansion. So when I talk about how people learn language or how do they recognize faces, we're not going to talk about much neurons and practically, but we will take about different brain areas and how they work. Then the assumption is bad is that everything we talk about in more functional ways can ultimately reduce down to large networks or neural system, and then in turn will ultimately reduce down to the specific behaviors of the specific neurons that we are looking at.